You are listening to API Gateways and Management, Architecting and Governing Your Digital Interface. Subscribe to keep up to date on our latest audiobooks. API Gateways and Management, Architecting and Governing Your Digital Interface. Chapter 1, The Digital Interface, an Introduction to APIs and the Need for Gateways. Imagine a world where every digital service operates independently, unable to communicate. Your favorite weather application couldn't pull real-time data from a meteorological agency. Your online shopping cart wouldn't be able to process payments through your bank. Your navigation app couldn't access up-to-the-minute traffic information. Such a world would be fractured, inefficient, and remarkably inconvenient. Fortunately, we live in a highly interconnected digital landscape, a reality made possible by an unsung hero of the Internet, the Application Programming Interface, or API. APIs are the invisible threads that weave together the fabric of our modern digital experience. They are the silent orchestrators behind countless daily interactions, enabling everything from simple smartphone applications to complex global supply chains. But as the number of these digital connections has exploded, so too has the need for a sophisticated guardian to manage, secure, and optimize them. This guardian is the API Gateway. What exactly is an API? The language of digital conversation. At its core, an API is a set of rules, protocols, and tools that allows different software applications to communicate with each other. Think of it as a standardized contract between two pieces of software, detailing the precise methods they can use to exchange information and fulfill requests. To truly grasp an API's function, consider a familiar scenario: dining at a restaurant. When you visit a restaurant, you don't walk into the kitchen and directly tell the chef how to prepare your meal, nor do you need to understand the intricate cooking process. Instead, you interact with a menu. The menu lists various dishes you can order, along with their descriptions and prices. You choose an item from the menu, and then a waiter takes your order to the kitchen. The kitchen then prepares your food, and the waiter brings it back to your table. In this analogy, you, the customer, are the client application, e.g., a mobile app, a website. The menu is the API documentation, showing what's available. The waiter is the API itself, taking your request to the kitchen and bringing back the response. The kitchen is the backend system that processes the request and provides the service, e.g., a server, a database, another application. You don't need to know how the kitchen operates. You just need to know what you can order and how to place the order. Similarly, an application doesn't need to understand the internal workings of another system. It just needs to know what requests it can make via the API and what kind of responses to expect. APIs in your daily life, you encounter APIs constantly without realizing it. Checking the weather. When your smartphone displays today's forecast, it's not making direct observations. Instead, your weather app uses an API to send a request to a weather service's servers. The service then sends back the current weather data, which your app then formats and displays. Online payments. Every time you use an online form to pay with a credit card or a digital wallet, the e-commerce website doesn't directly handle your sensitive financial information. It uses an API to securely transmit your payment details to a payment processing service, which then communicates with your bank. Log in with Google Facebook. These convenient buttons leverage APIs. When you click one, your application uses the respective social media API to securely verify your identity with Google or Facebook, granting your app access to basic profile information without you having to re-enter credentials. Mapping and ride-sharing apps. When you request a ride, the app uses mapping APIs to display your location, find nearby drivers, calculate routes, and estimate arrival times. These APIs are constantly exchanging data with GPS services, traffic monitors, and the ride-sharing company's own backend. Historically, software systems communicated in a variety of complex and often proprietary ways. The rise of the Internet, and particularly the World Wide Web, pushed for more open and standardized methods. Early forms like SOAP, Simple Object Access Protocol, provided structured communication, but it was the advent of REST, representational state transfer, that truly democratized API development. REST-TFL APIs, with their flexible and stateless nature, became the de facto standard, making it easier for developers to connect diverse systems using familiar web protocols. The API economy. Why do APIs matter so much? The proliferation and standardization of APIs have unleashed what is often referred to as the API economy. This isn't just a technical term. It reflects a fundamental shift in how businesses operate, innovate, and compete. Connectivity and interoperability. APIs break down digital silos. They enable disparate systems, whether within a single company or across multiple organizations, to seamlessly exchange data and functionality. This means your customer relationship management (CRM) system can talk to your marketing automation platform, which can in turn leverage a third-party email delivery service, all through APIs. Innovation and digital transformation. APIs allow companies to expose their core data and services in a controlled way, empowering external developers, partners, and even internal teams to build new applications and services on top of existing capabilities. This fosters rapid innovation. Think of how many apps integrate with Google Maps or Twitter. These are new businesses built on existing API foundations. Speed and agility. Instead of building every function from scratch, developers can reuse existing, proven services via APIs. Need to send a text message? Don't build your own SMS infrastructure. Integrate with a messaging API. This dramatically accelerates development cycles and allows companies to respond more nimbly to market demands. Microservices architecture. Modern software development often breaks down large applications into smaller, independent services known as microservices. APIs are the glue that holds these microservices together, allowing them to communicate and collaborate to deliver a complete application. Monetization and new business models. APIs can be monetized directly. Companies like Stripe, payment processing, or Twilio, communication services, earn revenue by providing API access to their specialized functionality. APIs also enable indirect monetization by broadening a product's reach or enhancing its ecosystem. Competitive advantage. Organizations that embrace APIs effectively can become more agile, build richer customer experiences, foster stronger partnerships, and unlock new revenue streams. In today's digital world, a robust API strategy is no longer a luxury but a competitive imperative. The tangled web. Challenges of API proliferation. While the benefits of APIs are immense, their very success can lead to significant challenges if not managed properly. As organizations expose more and more APIs, perhaps hundreds or even thousands, what started as a simple solution can quickly become an unmanageable mess. Imagine our restaurant kitchen, now with hundreds of waiters, APIs, taking orders directly from customers without any central coordination. Chaos would quickly ensue. This is precisely the problem many organizations face without an API gateway. Here are some of the critical challenges. Security nightmares. Each API endpoint becomes a potential entry point for attackers. Without a centralized security layer, ensuring consistent authentication, authorization, and threat protection across every single API is nearly impossible. Developers might implement security differently for each API, leading to inconsistencies, vulnerabilities, and an arduous audit process. Traffic chaos. What happens when an API suddenly experiences a massive surge in requests, perhaps a successful marketing campaign, or worse, a denial-of-service attack? Without a way to control traffic flow, rate limit individual users, or throttle abusive clients, backend services can quickly become overwhelmed, leading to outages and poor performance for legitimate users. Blind spots in monitoring and analytics. If APIs operate independently, gathering comprehensive data on their usage becomes a fragmented nightmare. It's difficult to get a holistic view of which APIs are most popular, who is using them, how they are performing, or where errors are occurring. This lack of visibility hinders troubleshooting, capacity planning, and strategic decision-making. Management mayhem. How do you ensure consistent policies, for example, data formatting, caching rules, or versioning strategies across all your APIs? How do you manage the lifecycle of an API from design to deployment to eventual deprecation? Without centralized governance, API management becomes a messy, inconsistent, and error-prone process. Developer frustration. For external third-party developers, discovering and understanding an organization's APIs can be a daunting task if they are scattered, poorly documented, and behave inconsistently. This poor developer experience can hinder adoption and stifle innovation. These challenges illustrate a clear need for a centralized control point, a sophisticated front door for all API interactions. This is precisely where the API Gateway provides its invaluable service. The unseen guardian. Enter the API Gateway. An API Gateway is a central entry point for all API requests. It acts as a single, unified interface that sits in front of your backend services, routing requests to the appropriate destination while also enforcing policies, enhancing security, and gathering critical insights. To return to our analogy, if the waiters are individual APIs, the API Gateway is the concierge or bouncer at the entrance of a high-end club, combined with the head waiter. Every guest API request seeking entry must pass through this central entity. The gateway's roles would include checking invitations, authentication, verifying the guest's identity and ensuring they are authorized to enter, enforcing dress code, policy enforcement, ensuring requests conform to specific rules before proceeding, counting heads, rate-limiting throttling, making sure the club doesn't get overcrowded or that a single guest isn't hogging all the space, directing guests, routing, guiding each guest to the correct part of the club or specific private room requested, scanning for prohibited items, threat protection, looking for malicious content or suspicious activity. The API Gateway doesn't directly do the work of the backend services, like mixing drinks or playing music, but it intelligently manages access to those services. It streamlines the flow, ensures security, optimizes performance, and provides invaluable oversight. The core promise of an API Gateway is to bring order to the potential chaos of a burgeoning API landscape. It provides centralized control, a single point to manage all API traffic and enforce unified policies, uniform policy enforcement, apply consistent security, traffic, and transformation rules across your entire API portfolio, enhanced security, a dedicated layer to protect your backend services from various threats, improved performance and scalability. Features like caching, load balancing, and efficient routing contribute to a faster, more reliable API experience. Better developer experience. A consistent and well-managed API layer makes it easier for developers to discover, understand, and integrate with your services. As we move forward, we will delve deeper into the intricate anatomy of an API Gateway, explore its rich array of features that extend far beyond simple routing, and understand how it forms the cornerstone of effective API management. By mastering the API Gateway, organizations can transform their digital interfaces from mere points of connection into powerful drivers of innovation and business success. An API Gateway is far more than just a simple pass-through. It's an intelligent traffic controller, a diligent security guard, and a meticulous data inspector, all rolled into one. To understand its power and why it's indispensable in modern digital architectures, we first need to dissect its core components and trace the journey of an API request as it passes through this crucial intermediary. The gateway's place, reverse proxy and policy enforcement point. At its most fundamental level, an API gateway operates as a reverse proxy. Imagine a large corporation with many different departments, each handling specific tasks. You, as an external visitor, don't dial the direct number for each department. Instead, you call a main reception number. The receptionist takes your call, understands your request, and then precisely connects you to the right department. The receptionist hides the complexity of the internal phone directory and ensures you reach the correct destination. In the digital world, the API Gateway acts as that receptionist. Your client application, like a mobile app or a website, sends an API request to the gateway's public address, not directly to the specific backend service that will fulfill the request. The gateway then intelligently forwards that request to the appropriate internal service, shielding your backend architecture from direct exposure to the public internet. This offers immediate security benefits and vastly simplifies the client's interaction. But the gateway is not just a passive forwarder of messages. It is also a policy enforcement point, PEP. This means that at various stages of the request and response flow, the gateway actively applies a set of predefined rules and actions. These policies might dictate who can access what, how much traffic is allowed, what data format is expected, or how errors should be handled. It's the central checkpoint where security, traffic management, and data manipulation rules are enforced consistently across all the APIs it manages. Commonly, an API gateway is deployed right at the edge of an organization's internal network or within a cloud environment, sitting squarely between the external world, clients, partner applications, and the internal backend services, microservices, legacy applications, databases, etc. This strategic placement allows it to intercept and process every single API call before it reaches the core systems. The journey of an API request, through the gateway and back. To truly appreciate the multifaceted role of an API gateway, let's trace the typical path an API request takes, highlighting the various checkpoints and actions performed along the way. Request initiated by client. The journey begins when a client application, e.g., your smartphone app, a web browser, another server-side application, needs to access a specific functionality or data from your services. It sends an API request, typically an HTTP request with a specified URL, method, GET, POST, PUT, delete, headers, and potentially a body, payload directly to the API gateway's public endpoint. Gateway receives request. The API gateway is the first point of contact. Upon receiving the incoming request, it begins its work by examining various aspects like the request path, HTTP method, and headers, pre-processing policies before backend interaction. This is where the gateway starts applying its intelligence. Before even thinking about sending the request to a backend service, it performs a series of crucial checks based on the policies configured for that specific API and client. Authentication. Who are you? The gateway verifies the client's identity. This might involve validating an API key, decrypting and validating an OAuth 2.0 token like a JWT, or confirming credentials. If the client cannot be authenticated, the gateway promptly rejects the request with an appropriate error, e.g., unauthorized. Authorization. Are you allowed to do that? Even if authenticated, the client might not have permission to access a specific resource or perform a particular action. The gateway checks the client's permissions against the requested operation. If unauthorized, the request is rejected, e.g., forbidden. Rate limiting and throttling. Are you sending too many requests too quickly? To protect backend services from being overwhelmed and ensure fair usage, the gateway monitors the rate of requests from each client. If a client exceeds its predefined limit, e.g., 100 requests per minute, subsequent requests are temporarily blocked or slowed down, throttled. This prevents abuse and maintains service stability. Input validation. Is the request well-formed? The gateway can validate the structure and content of the request payload or parameters against a predefined schema. This catches malformed or malicious inputs early, preventing faulty data from reaching backend services. Request transformation. Does this request need modification before being sent to the backend? Sometimes, the external API format accepted by the gateway might differ slightly from what the internal backend service expects. The gateway can transform request headers, query parameters, or even the entire payload format, e.g., translating between XML and JSON to ensure compatibility. Routing. After all pre-processing policies have been successfully applied, the gateway determines which specific backend service should handle the request. This routing decision is typically based on the API's URL path, but it can also be influenced by HTTP headers, query parameters, or even the client's identity. For example, requests to user's profile might go to a user service, while requests to products catalog might go to a product service. Proxying to backend service, the gateway then acts as a client itself, forwarding the potentially transformed request to the appropriate internal backend service. This communication between the gateway and the backend services is often within a secure, private network, further protecting the internal infrastructure. Backend processes request and sends response. The backend service receives the request, processes it, retrieves or updates data as required, and then sends a response back to the API gateway. Post-processing policies before client response. Before sending the final response back to the original client, the gateway can apply another set of policies. Response transformation. Does this response need modification before being sent to the client? Similar to request transformation, the gateway can modify the response payload, e.g., filtering out sensitive internal data, adding standard headers, or converting data formats for the external consumer. Caching. Can we serve this response faster next time? For frequently requested, non-volatile data, the gateway can cache the backend service's response. Subsequent identical requests can then be served directly from the cache, significantly reducing latency and load on backend services. Logging and analytics. Let's record what just happened. The gateway logs details about the transaction request details, response status, latency, client information, etc. This data is crucial for monitoring API usage, performance, billing, and troubleshooting. Fault injection circuit breaking, advanced. In some cases, the gateway might also implement strategies to gracefully handle backend service failures, such as returning a cached response, a default response, or triggering a circuit breaker to prevent cascading failures. Gateway sends response to client. Finally, the API gateway sends the process data back to the original client application, completing the journey. From the client's perspective, it feels like it communicated directly with the service, unaware of the complex choreography performed by the gateway. Clarifying its role, gateway versus similar technologies. The functionalities of an API gateway can sometimes sound similar to other networking or security tools. It's important to understand the distinctions. API gateway versus load balancer. A load balancer distributes incoming network traffic across multiple identical instances of a single application or service. Its primary goal is to ensure high availability and responsiveness by preventing any one server from becoming overwhelmed. It operates primarily at the transport layer, Layer 4, or sometimes HTTP layer, Layer 7, for basic routing. An API gateway, however, routes requests to different backend services, which may or may not be load balanced internally, based on the specific API endpoint being called, and applies rich, application-level policies on each request. A common architectural pattern is for an API gateway to sit behind a load balancer, with the load balancer distributing traffic among multiple instances of the gateway itself for high availability. API gateway versus firewall. A firewall acts as a network security system that grants or denies network access based on predefined security rules. It operates at lower network layers, L3, L4, primarily inspecting IP addresses and port numbers. It's like the outer security perimeter of a building, controlling who can even approach the premises at a basic network level. An API gateway operates at the application layer, L7, understanding the content and context of API requests. It can inspect specific API keys, validate JSON payloads, apply rate limits per user, and transform data. It's like the security guard at an internal office door who checks your ID, your credentials for that specific department, and only allows you in if you're on the authorized list and behaving appropriately. While both contribute to security, their scope and method of operation are different. API gateway versus service mesh. This is an important distinction in modern microservices architectures. A service mesh, e.g., Istio, Linkerd, manages communication between microservices within your internal network or cluster, often called east-west traffic. It provides capabilities like traffic management, observability, and security for internal service-to-service calls. It helps microservices find each other, communicate reliably, and report their health. Think of it as the internal plumbing and traffic control within a factory. An API gateway manages traffic coming from outside your network into your services, often called north-south traffic. It's the public front door for your APIs. While a service mesh handles the internal complexities of microservice interaction, the API gateway handles the external exposure and management of those services to the wider world. They are complementary. An API gateway is the entry point, and a service mesh ensures smooth intraservice communication once traffic is inside. Understanding the anatomy of an API gateway reveals its critical role beyond simple routing. It is the central nervous system for your API ecosystem, enabling comprehensive control over security, traffic flow, and data transformation, all while providing invaluable insights into API health and usage. In the following chapters, we will delve deeper into each of these powerful features and explore how they contribute to effective API management. Chapter 3: More than just a proxy. Essential features of an API gateway. As we explored in the previous chapter, an API gateway is fundamentally a reverse proxy and a policy enforcement point. However, to truly appreciate its value and understand why it has become an indispensable component in modern architectures, we must move beyond these basic definitions. A robust API gateway offers a rich suite of features that address critical challenges in API security, performance, and management. It transforms a simple traffic director into a comprehensive control plane for your digital interfaces. These essential features can be broadly categorized, though many overlap and work in concert to deliver a coherent and powerful solution. Security features. Fortifying your digital front door. Security is arguably the most critical function of an API gateway. By acting as the sole entry point, it provides a unified layer of defense, shielding your backend services from the direct gaze and potential threats of the internet. Authentication. This is the process of verifying a client's identity. The gateway can enforce various authentication mechanisms. API keys, a simple token provided by the client with each request. The gateway validates the key against a registry to ensure it's legitimate and active. While easy to implement, API keys offer limited security on their own and don't typically convey user identity. OAuth 2.0/OpenID Connect, OIDC, the industry standard for secure delegated authorization. The gateway validates access tokens, e.g., JSON Web Tokens or JWTs, issued by an identity provider, IDP. This is highly flexible, allowing for different levels of access and linking to specific user identities. Mutual TLS, MTLS. For highly sensitive internal or partner APIs, MTLS establishes a secure connection where both the client and the server, gateway, authenticate each other's digital certificates. By centralizing authentication, inconsistent and potentially weak security implementations on individual backend services are avoided. Authorization. Once authenticated, the gateway determines what actions the identified client is allowed to perform. Role-based access control, RBAC, clients or users are assigned roles, e.g., admin, read-only, premium user, and the gateway enforces rules based on these roles. Attribute-based access control, ABAC. More granular authorization, where access decisions depend on multiple attributes about the user, resource, or environment, e.g. Only users from country X can access resource Y during business hours. The gateway prevents unauthorized access to sensitive endpoints or specific data fields, acting as a crucial gatekeeper. Threat protection. Beyond standard access control, gateways offer advanced capabilities to defend against various attacks. DDoS brute force protection. By monitoring request patterns and IP origins, the gateway can detect and mitigate distributed denial of service, DDoS, attacks or brute force login attempts by blocking or slowing down suspicious traffic. SQL injection XSS protection. Many gateways include Web Application Firewall, WAF, capabilities, inspecting request payloads for common attack patterns like SQL injection or cross-site scripting, XSS, and blocking malicious requests. Schema validation. Enforcing strict data format rules ensures that only legitimate, well-structured requests reach the backend, preventing attacks that exploit malformed inputs. CORS, Cross-Origin Resource Sharing, Management. Properly configured CORS policies on the gateway prevent unauthorized websites from making requests to your APIs, mitigating certain types of web-based attacks. II. Traffic management. Orchestrating the flow. Efficiently managing API traffic is crucial for performance, reliability, and ensuring fair access. API gateways offer sophisticated tools to control how requests flow through your system. Rate limiting and throttling. Rate limiting prevents abuse and ensures fair usage by restricting the number of requests a client can make within a specified time frame, e.g., 100 requests per minute per API key. If the limit is exceeded, subsequent requests are typically rejected with a 429 too many requests error. Throttling. Similar to rate limiting, but often involves delaying responses rather than outright rejecting them, to smooth out traffic spikes rather than block bursts. These controls protect backend services from being overwhelmed and help ensure a consistent quality of service for all consumers. Load balancing. While a dedicated load balancer might sit in front of the gateway itself, a gateway can also perform rudimentary load balancing across multiple instances of a specific backend service. This can involve simple round-robin distribution or more sophisticated algorithms based on server load or response times. Caching. For idempotent, meaning repeated requests produce the same result, and frequently accessed data, the gateway can cache responses. When a subsequent identical request comes in, the gateway can serve the response directly from its cache, bypassing the backend service entirely. This significantly reduces latency, decreases load on backend systems, and improves overall API performance. Circuit breaking. This pattern helps prevent cascading failures in a microservices architecture. If an API gateway detects that a backend service is consistently failing or very slow, it can trip the circuit breaker, temporarily stopping all requests to that service. Instead, it might return a default error response or a cached response, allowing the service time to recover without being hammered by continuous requests. Request routing. The core function of directing requests to the correct backend service based on URL path, hostname, HTTP method, or other criteria. More advanced gateways support dynamic routing, traffic splitting, e.g., sending 10% of traffic to a new version of an API for A/B testing, and canary releases. III, request response transformation, adapting to diverse consumers. APIs are often consumed by a variety of clients, each with potentially different needs regarding data formats, headers, or security protocols. An API gateway acts as an invaluable translation layer. Protocol translation bridging. A gateway might expose REST-TFL APIs to consumers while internally communicating with backend services using different protocols like SOAP, gRPC, or even Kafka. Data transformation. Converting data formats between front-end and backend, e.g., XML to JSON or vice versa. This allows backend services to maintain their preferred internal data formats while presenting a standardized, user-friendly format to external consumers. Header manipulation, adding, removing, or modifying HTTP headers. This can be useful for injecting security tokens, logging IDS, or ensuring compliance with specific client requirements. Payload modification filtering, modifying the content of the request or response body. For example, sensitive fields can be automatically filtered out of responses before they are sent to external consumers, or specific data elements can be added to requests for internal logging. Versioning, managing different API versions, e.g., api.example.com/v1/users versus api.example.com/v2/users. The gateway can direct requests to the appropriate backend service version, allowing for staged rollouts and graceful deprecation without breaking existing client integrations. IV. Monitoring and analytics. Gaining insights into API usage. A central API gateway is a goldmine of operational data. It can capture comprehensive metrics on every API call, providing invaluable insights into performance, usage, and errors. Logging, detailed logs of every request, including source IP, client ID, request path, response status, latency, and more. These logs are crucial for debugging, auditing, and security analysis. Metrics and dashboards. Collecting and aggregating metrics like request volume, response times, error rates, throughput, and cache hit rates. These are often presented in real-time dashboards, allowing operations teams to quickly identify trends, bottlenecks, or anomalies. Alerting, configuring alerts based on predefined thresholds, e.g., if the error rate for a specific API exceeds 5% in a 5-minute window. This enables proactive issue resolution. Usage tracking and billing, tracking API consumption per client or per application, which is essential for understanding commercial API product usage, enabling tiered access, or facilitating billing models. Developer experience features, building a thriving ecosystem. While often considered part of a broader API management platform, the API Gateway plays a crucial role in enabling a positive developer experience by providing the backbone for developer-facing tools. Integration with developer portals. By providing structured metadata about APIs and handling authentication authorization, the Gateway facilitates the automatic generation of API documentation and enables self-service onboarding for developers through a developer portal. Discovery and documentation. Supporting API documentation formats like OpenAPI Swagger that can be served or integrated with the Gateway ensures developers can easily understand how to use your APIs. API productization. The Gateway can support grouping APIs into products or plans, each with different access tiers, rate limits, and features, making it easier to expose and monetize sets of APIs. The combination of these features makes the API Gateway a cornerstone of any robust API strategy. It moves far beyond a simple networking device, evolving into a strategic tool that enables security, optimizes performance, simplifies management, and fosters innovation by providing a controlled and powerful interface to your digital assets. The next chapter will explore how these Gateway capabilities fit into the broader concept of API management, covering the entire lifecycle of an API from design to deprecation. Chapter 4. The Art of API Management, from Design to Deprecation. In the preceding chapters, we explored what APIs are, why they are essential to the modern digital economy, and how an API Gateway serves as a critical front door, centralizing security and traffic management. However, deploying an API Gateway, while foundational, is just one piece of a much larger puzzle. To truly harness the power of APIs and ensure their long-term success, organizations must embrace a holistic approach known as API management. API management encompasses the entire lifecycle of an API, from its initial conception and design, through its development, deployment, ongoing operation, and eventual deprecation. It's about more than just technology. It involves strategy, governance, processes, and people, all working together to transform APIs from mere technical interfaces into valuable business products. Why API management is essential. Beyond the Gateway scope, think of it this way. The API Gateway is like a state-of-the-art manufacturing plant. It efficiently processes raw materials, API requests, applies quality control, security, and transformation policies, and ensures that finished goods responses are delivered precisely where they need to go. But a factory, however advanced, needs a comprehensive business strategy. What products should we make? Who are our customers? How do we market and distribute? How do we ensure consistent quality over time? How do we handle product revisions or discontinuation? Without a broader API management strategy, even the best API Gateway and backend services can fall short. The challenges identified in Chapter 1, such as security inconsistencies, lack of visibility, and developer friction, reemerge if there isn't a systematic approach to govern the entire API ecosystem. API management is the antidote to these complexities. It converts a collection of individual APIs into a managed product portfolio. The API lifecycle, a continuous journey. API management platforms and practices typically support a continuous lifecycle, ensuring that APIs remain valuable and secure throughout their existence. Let's delve into the key stages. 1. API strategy and design. This is where the API journey begins, long before a single line of code is written. Business drivers. What business problem is this API solving? What value does it create for internal teams, partners, or external developers? Is it for revenue generation, efficiency, or rapid innovation? Audience and productization. Who will consume this API? How will it be bundled and presented as a product? What are the target service level agreements, SLAs? Design first. Instead of coding first and documenting later, a design-first approach is paramount. This involves defining the API's interfaces, data models, error handling, and security mechanisms using standardized specifications like OpenAPI, formerly Swagger. This ensures consistency, clarity, and reusability across your API portfolio. Governance. Establishing clear guidelines and standards for API design, naming conventions, authentication methods, error codes, and documentation for all APIs across the organization. This prevents API sprawl and ensures a consistent developer experience. How API management tools help. Design tools, often integrated into API management platforms, can help model APIs, validate OpenAPI specifications, and enforce internal governance policies, acting as a central repository for API definitions. 2. API development and testing. Once an API is designed, the focus shifts to bringing it to life. Implementation. Backend developers interpret the API design specification from the previous stage and implement the actual business logic and data access required to fulfill API requests. Mocking and sandbox environments. Developers, both internal and external, can use mock APIs, simulated responses based on the OpenAPI spec, to begin their integration work even before the real backend services are fully developed. This accelerates parallel development. Automated testing. Rigorous testing is crucial to ensure an API functions as expected, handles errors gracefully, and remains performant under load. This includes functional testing, security testing, performance testing, and regression testing. How API management tools help. Platforms can provide mock servers, integrate with testing frameworks, and offer developer sandboxes that mirror production environments, facilitating faster development and more thorough testing. 3. API deployment and publishing. This stage is about making the API available for consumption. Gateway configuration. The API gateway is configured with the routing rules, security policies, rate limits, and transformations that apply to the newly developed API, as discussed in Chapter 3. Developer Portal. This is a self-service website that serves as the public face of your API program. It's where developers discover APIs, browse interactive documentation, often generated automatically from OpenAPI specs, sign up for API keys, manage their applications, and test API calls. A well-designed developer portal is critical for adoption and a positive user experience. Subscription management. API management platforms allow organizations to define different tiers of access, e.g., free, premium, enterprise, manage developer applications, and provision API keys or credentials. Onboarding, streamlining the process for new developers to register, get access, and start using your APIs. How API management tools help. These platforms typically include a fully featured developer portal, tools for managing client applications and API keys, and seamless integration with the API gateway for publishing APIs with applied policies. 4. API runtime governance and security. Once published, APIs are actively managed to ensure their ongoing security, performance, and compliance. This is where the API gateway plays its most prominent daily role. Policy enforcement. The API gateway centrally enforces all defined policies: authentication, authorization, rate limiting, data transformation, caching, and threat protection, just as discussed in Chapter 3. Traffic shaping. Managing peak loads, ensuring fair access, and preventing service outages due to traffic surges. Security monitoring. Continuous scanning and analysis of API traffic for anomalies or potential attacks. How API management tools help. The API gateway itself is the direct enforcer, but the broader API management platform provides the consoles and tools to define, update, and monitor these policies across your entire API portfolio. 5. API monitoring and analytics. Understanding how APIs are being used and how they are performing is vital for continuous improvement and strategic decision-making. Performance monitoring, tracking key metrics like latency, error rates, throughput, and uptime to ensure APIs are meeting their SLAs. Usage analytics, gaining insights into who is using which APIs, how frequently, from where, and for what purpose. This data is invaluable for understanding API popularity, identifying new opportunities, and informing future development. Security auditing, monitoring for suspicious activities, failed authentication attempts, and policy violations. Billing monetization, if applicable, tracking API consumption for commercial purposes to generate invoices or manage usage tiers. How API management tools help. Most platforms include robust analytics dashboards, reporting features, and alerting mechanisms that leverage the detailed logs collected by the API gateway. 6. API versioning and evolution. APIs are rarely static. As business needs change, new features are added, or underlying systems evolve, APIs must adapt. Versioning strategies. Implementing clear strategies for handling changes, such as URL versioning, e.g., V1 users, V2 users, header versioning, or content negotiation. Backward compatibility. Striving to make changes without breaking existing client integrations. When breaking changes are unavoidable, providing clear migration paths and generous transition periods. Iteration and improvement. Continuously gathering feedback from developers, monitoring usage data, and iterating on API designs and functionalities based on real-world insights. How API management tools help. The gateway can facilitate concurrent hosting of multiple API versions, and the platform can assist in communicating version changes and maintaining documentation for different versions. 7. API deprecation and retirement. Just like any product, APIs eventually reach the end of their useful life. Phased deprecation, a graceful process of discontinuing an API, which involves notification, clearly communicating the deprecation timeline, reasons, and instructions for migration to newer versions to all affected developers well in advance. Reduced support, gradually scaling back support for the deprecated version while still keeping it operational for a defined period. Monitoring usage, tracking which clients are still using the deprecated API to provide targeted assistance. Retirement, fully removing the API from service after the deprecation period has ended. How API management tools help. Platforms can help automate notification processes, track usage of deprecated APIs, and facilitate the complete removal from the developer portal and gateway when appropriate. The holistic view. The art of API management lies in orchestrating all these stages seamlessly. It's about establishing repeatable processes, applying consistent governance, and leveraging the right tooling, with the API gateway as its central enforcement point, to build a thriving, secure, and evolution-ready API ecosystem. By mastering API management, organizations can move beyond simply exposing digital capabilities to strategically productizing them, unlocking new markets, fostering innovation, and ultimately driving their digital transformation journey forward. Chapter 5: Building a Thriving API Ecosystem. Developer portals, documentation, and discovery. We've established that APIs are the connections that drive digital business, and API gateways are the sophisticated infrastructure managing these connections. But what makes an API truly successful? Is it merely its technical elegance, its speed, or its robust security? While these are undoubtedly crucial, the ultimate success of an API, its adoption usage, and the innovation it enables, often hinges on one critical factor: the developer experience (DX). An API, no matter how powerful, is useless if developers struggle to find it, understand it, integrate it, or get support when they encounter issues. This is where the concept of an API ecosystem comes into play. It encompasses not just the technical interfaces themselves, but all the tools, resources, community, and support mechanisms that enable developers to efficiently build on your APIs. Building a thriving API ecosystem means treating your API consumers, particularly developers, as your primary customers. The paramount importance of developer experience, DX. Imagine buying a complex new piece of equipment for your home or business. If it comes without clear instructions, if its buttons aren't labeled, if troubleshooting guides are non-existent, and customer support is unreachable, you'd quickly become frustrated. You might even abandon the product, no matter how revolutionary its underlying technology. The same applies to APIs. For developers, a poor experience might manifest as difficulty finding the relevant API documentation, inadequate or outdated examples, confusing error messages from the API gateway or backend, lack of clear communication about changes or issues, a fragmented process for obtaining API keys or managing applications, no clear path to ask questions or report bugs. These pitfalls directly lead to developer frustration, slower integration times, increased support costs, and ultimately, low adoption rates. Conversely, a fantastic developer experience fosters loyalty, encourages experimentation, and accelerates the integration of your APIs into new and innovative applications. Companies like Stripe and Twilio are often lauded not just for their robust APIs, but for their exemplary developer experiences, which have been pivotal to their success. So, how do we craft such an experience? It starts with a comprehensive developer portal, backed by stellar documentation and clear discovery pathways. The developer portal, your API's digital showroom. The developer portal is the central hub for your API ecosystem. It's a dedicated website that serves as the self-service front door for anyone looking to build on your APIs. Think of it as an online showroom and a comprehensive support center specifically tailored for API consumers. A well-designed developer portal typically offers the following functionalities: API catalog and discovery, a clear, searchable list of all available APIs, often categorized by function or business unit. This helps developers quickly find what they need. Self-service registration and onboarding. Developers can easily sign up, create an account, and get immediate access to API keys. This streamlines the process and reduces manual intervention. API key and application management. Once registered, developers can manage their assigned API keys, create and manage multiple applications, each with its own set of keys, reset keys, and track their usage. The API gateway integrates here by validating these keys for every incoming request. Interactive API documentation. This is arguably the most critical feature. The portal hosts comprehensive, up-to-date documentation for every API, often generated automatically from OpenAPI specifications. This documentation typically includes endpoint details, descriptions of each API endpoint, its purpose, accepted HTTP methods, GET, POST, etc., and URL paths. Request response schemas, detailed specifications of input parameters, query, header, body, and expected output structures, often with examples. Authentication requirements, clear instructions on how to authenticate requests, e.g., where to place the API key, how to construct OAuth tokens. Error codes, a comprehensive list of possible error responses with explanations and troubleshooting tips. Try it out consoles, interactive tools that allow developers to make live API calls directly from the browser within the documentation interface, using their own API keys. This provides instant feedback and accelerates testing. Tutorials and how-to guides, step-by-step guides for common use cases, helping developers quickly integrate the API into their applications. Software development kits, SDKs, and code samples, pre-built libraries or code snippets in various programming languages, e.g., Python, Java, Node.js, that simplify interaction with the API, reducing integration time. Analytics and usage metrics. For developers themselves, the portal can provide insights into their own API consumption, including call volume, error rates, and latency. This helps them monitor their usage and debug their integrations. Support and community. Links to support channels, email, ticketing systems, community forums, FAQs, and perhaps even a changelog or a blog for API updates. The power of documentation, guiding developers to success. While the developer portal is the wrapper, documentation is the true substance that educates and enables developers. High-quality documentation is paramount. It should be. accurate and up-to-date. Nothing is more frustrating than incorrect information. Documentation must reflect the current state of the API and its policies, which is why automated generation from a single source of truth, like an open API spec that also configures the API gateway, is ideal. Clear and concise, use plain language, avoid unnecessary jargon, get straight to the point. Comprehensive, cover all aspects: authentication, request formats, response structures, error handling, rate limits, and best practices. Actionable, include practical examples, code snippets, and try-it-out functionality that developers can immediately use. Well-organized and searchable. Easy navigation and powerful search capabilities help developers find specific information quickly within the portal. Many API management platforms streamline documentation. By using a design-first approach, as discussed in Chapter 4, and defining your APIs using Open API Swagger specifications, you can automatically generate interactive documentation directly on your developer portal. This ensures consistency between your API design, your gateway configuration, and your developer-facing guides. Discovery, making your APIs findable. Even the best API and documentation are useless if no one knows they exist. API discovery is about making your APIs easily findable by the right audience. Internal discovery. For large organizations that embrace microservices, internal discovery is crucial. Developers within different teams need a centralized catalog, often part of an internal developer portal, to find and reuse existing internal APIs, preventing redundant development. External discovery. For public APIs, marketing and search engine optimization, SEO play a role. Listing your APIs on public API marketplaces like RapidAPI or Postman API Network can significantly increase visibility. Press releases, blog posts, and active participation in developer conferences and online communities also contribute to discovery. The developer portal serves as the primary external discovery mechanism, guiding potential consumers to the detailed information they need. Fostering a community and providing support. A successful API ecosystem isn't just about providing tools, it's about building relationships. Community forums Q&A. Dedicated spaces where developers can ask questions, share solutions, and help each other. This fosters a sense of community and can significantly reduce direct support requests. Direct support channels. Clear pathways for developers to get help when they encounter complex issues that cannot be resolved through documentation or forums. This could be email, a ticketing system, or even a dedicated Slack Discord channel. API evangelism. Dedicated roles or teams that act as advocates for your APIs, engaging with the developer community, creating content, speaking at events, and gathering feedback. Feedback mechanisms. Provide clear ways for developers to submit feedback, report bugs, or suggest new features. Listening to your API consumers is vital for continuous improvement. By investing in a robust developer portal, comprehensive documentation, and a supportive community, organizations signal their commitment to their API consumers. This commitment reaps rewards in terms of faster adoption, decreased support burden, innovative applications built on your offerings, and a vibrant partner ecosystem. Ultimately, a strong API ecosystem translates directly into stronger business outcomes, ensuring that the valuable APIs managed by your API gateway are not just technically sound, but widely adopted and deeply valued. Chapter 6, Fortifying Your Digital Front Door, API Security Best Practices. In a world increasingly driven by interconnected digital services, APIs have become prime targets for malicious actors. Every API endpoint acts as a potential new entry point into an organization's systems and data. A single vulnerability in an API can expose sensitive customer information, lead to service disruptions, inflict significant financial losses, and severely damage a company's reputation. Therefore, API security is not merely a feature. It is an absolute imperative. The API gateway, by virtue of its position as the single entry point for all API traffic, naturally becomes the primary line of defense in an API security strategy. It's like the fortified perimeter of a castle, designed to scrutinize every visitor before they can even set foot inside the main grounds. Why API security is more critical than ever. Consider the sheer volume and sensitivity of data flowing through APIs today. Financial transactions, personal health information, proprietary business logic, and critical infrastructure controls are all exposed via APIs. This broad exposure creates a fertile ground for various attack types: data breaches, unauthorized access to and exfiltration of sensitive data, denial of service, DDoS, overwhelming API endpoints to make services unavailable, injection attacks, malicious code injected through API inputs to manipulate backend systems, broken authentication authorization, exploiting flaws in identity verification or permission checks, credential stuffing, using stolen username password pairs from other breaches to gain unauthorized API access. Organizations face not only the direct consequences of an attack, but also potential regulatory fines, e.g., GDPR, HIPAA, legal liabilities, and irreparable damage to brand trust. A strong, multi-layered security approach, with the API gateway at its core, is therefore non-negotiable. The API gateway as your primary security enforcer. As discussed in Chapter 3, the API gateway centralizes many critical security functions, providing a consistent and robust defense layer that would be difficult and error-prone to implement on each individual backend service. Authentication, knowing your visitor. The first step in any security process is knowing who is trying to access your API. The API gateway excels at enforcing various authentication mechanisms. API keys. While simpler, API keys, often long, randomized strings, are typically passed in headers or query parameters and serve as a basic identifier. The gateway validates if the key is legitimate and active. Best practice. Use API keys for basic identification and rate limiting, but not for sensitive authorization. OAuth 2.0 and OpenID Connect, OIDC. These are the modern standards for secure delegated authorization. The gateway intercepts the request, validates the access token, often a JSON Web Token or JWT, and extracts the user's identity and permissions. This offloads the token validation from backend services and ensures a consistent security posture. Best practice. For user-facing APIs, prefer OAuth 2.0 OIDC as they provide robust, standardized, and scalable authentication mechanisms. Mutual TLS, MTLS. For highly sensitive APIs, especially in B2B or internal communications, MTLS ensures that both the client and the server, gateway, authenticate each other using digital certificates. This provides strong identity verification and ensures encrypted communication. Best practice. Implement MTLS for high-security internal services or trusted partner integrations. Authorization. Verifying permissions. Once a client's identity is established, the gateway determines what actions that client is permitted to perform. Role-based access control, RBAC. The gateway can enforce access rules based on the user's assigned role, e.g., an admin role can access all endpoints, while a viewer role can only retrieve data. Attribute-based access control, ABAC. More granular control is possible where the gateway makes authorization decisions based on a combination of contextual attributes, such as user location, time of day, data sensitivity, or specific resource properties. This prevents unauthorized access to specific data fields or endpoints. Best practice. Implement fine-grained authorization. Apply the principle of least privilege, granting only the minimum access required for a client to perform its function. Rate limiting and throttling, controlling the flow. These controls are not just for performance, they are formidable security tools. By limiting the number of requests from a specific client or IP address within a time window, the gateway can effectively mitigate denial of service, DDoS, attacks, and prevent brute force attacks, e.g., guessing API keys or user passwords. It also prevents individual malicious or runaway applications from degrading service for all other legitimate users. Best practice. Configure realistic and dynamic rate limits based on typical usage, distinguishing between authenticated and unauthenticated users, and different service tiers. Input validation and data protection. Sanitizing and securing payloads. The gateway can act as a crucial filter for data traversing your APIs. Schema validation. Enforcing strict validation of incoming request payloads against predefined open API schemas. This prevents attacks like mass assignment, where an attacker tries to create or modify fields they shouldn't have access to, and generally reduces the attack surface by ensuring only expected data types and formats are processed. Injection prevention. Inspecting request parameters and body content for malicious code patterns associated with SQL injection, cross-site scripting XSS, XML external entities XXE, and command injection. Response data filtering transformation. Before sending responses back to the client, the gateway can filter out or mask sensitive data, e.g., credit card numbers, personally identifiable information, PII, internal system details, that should not be exposed externally. Best practice: validate all inputs at the gateway. Never trust unvalidated input. Never return sensitive internal details in API responses that aren't strictly necessary for the client. Threat protection and web application firewall (WAF) capabilities. Many API gateways incorporate features similar to a web application firewall (WAF) to detect and block common web-based attacks. These features protect against vulnerabilities listed in the OWASP API Security Top 10, such as Broken Object Level Authorization, BOLAS, where a user can access objects they shouldn't, often by simply changing an ID in the URL. A gateway's policy can enforce that only the owner of an object can access it. Broken Function Level Authorization, BFLA, where a standard user can access administrative or privileged functions. Security misconfiguration, ensuring adherence to security best practices and proper configurations. The gateway can analyze traffic for suspicious patterns, unusual request sizes, or attempts to exploit known vulnerabilities. Encryption in transit, securing the communication channels. While largely standard today, enforcing and managing secure communications centrally is vital. HTTPS TLS enforcement. The gateway ensures all communication to and from it is encrypted using HTTPS and strong TLS protocols. This protects data from eavesdropping and tampering. It can also manage the TLS certificates, simplifying their handling for multiple backend services. Best practice: always enforce HTTPS. Disable old, vulnerable TLS versions and weak ciphers. Logging and auditing, your security footprint. The API gateway's central position means it can capture comprehensive logs for every single API call. These logs provide an invaluable audit trail for forensic analysis in case of a security incident. They enable real-time security monitoring for suspicious activities or policy violations. Integrating these logs with a security information and event management (SIEM) system allows for centralized anomaly detection and threat intelligence. Best practice: ensure detailed logging is enabled for all API activity. Store logs securely, protect them from tampering, and regularly review them for anomalies. Beyond the gateway, a multi-layered approach to API security. While the API gateway is a crucial linchpin, API security is fundamentally a shared responsibility and requires a defense-in-depth strategy. Security by design. Security must be considered from the very beginning of the API design phase, Chapter 4. Don't bolt it on as an afterthought. Think about the attack surface, data sensitivity, and authorization requirements upfront. Backend services hardening. The gateway protects the front, but backend services must also be inherently secure. This includes secure coding practices, regular vulnerability patching, isolating services, and implementing internal firewalls. The gateway handles external threats, but internal threats or compromised services still need internal protections. Network security. Utilize firewalls, network segmentation, and virtual private clouds, VPCs, to ensure that only the API gateway is publicly accessible, and backend services are isolated in private networks. Secrets management. Securely store and manage API keys, database credentials, and certificates using dedicated secrets management solutions, rather than embedding them directly in code. Continuous security testing. Regularly perform penetration testing, vulnerability scanning, static application security testing, SAST, on code, and dynamic application security testing, DAST, on running APIs. Incident response plan. Have a clear, well-rehearsed plan for how to detect, respond to, and recover from an API security incident. In essence, an API gateway provides the robust security enforcement capabilities that are vital for protecting your digital assets. By centralizing authentication, authorization, traffic management, and threat detection, it prevents many common attacks and enforces consistent security policies uniformly. When combined with a holistic, security by design, mindset, and other layers of defense throughout your architecture, your API gateway creates a powerful, resilient digital front door, safeguarding your valuable data and ensuring the trustworthiness of your API ecosystem. Chapter 7, Keeping the Lights On. Operational Excellence, Monitoring, and Scalability. An API gateway is a powerful tool for managing and securing your APIs, but its true value is realized only when it operates reliably, efficiently, and with the capacity to handle fluctuating demands. This crucial aspect falls under the umbrella of operational excellence, which encompasses the principles and practices necessary to ensure that your API ecosystem remains robust, responsive, and available around the clock. Operational excellence for APIs hinges on three core pillars: proactive monitoring, intelligent logging, and built-in scalability and resilience. When these elements are meticulously implemented, your API gateway acts not just as a traffic cop, but also as a watchful sentinel and a powerhouse capable of growing with your digital business. Operational excellence, the foundation of reliable APIs. Operational excellence is about more than just keeping systems running. It's about optimizing their performance, anticipating issues, and responding effectively to maintain business continuity. For API gateways, this means reliability, ensuring APIs consistently perform as expected without unexpected downtime or errors. Performance, delivering responses quickly and efficiently, meeting latency targets. Efficiency, optimizing resource utilization and minimizing operational costs. Proactive issue resolution, identifying and addressing potential problems before they impact users. Automation, automating deployment, scaling, and recovery processes to reduce manual effort and human error. Consistency, applying consistent operational standards across all APIs. The API gateway is uniquely positioned to achieve these goals because it sits directly in the path of all API traffic, making it an ideal point for observation, control, and intelligent resource management. Monitoring, your API's vital signs. Just like monitoring a patient's vital signs in a hospital, continuously monitoring your API gateway and the APIs it manages is paramount. It provides real-time visibility into the health, performance, and behavior of your digital interface. Effective monitoring allows you to detect issues early, identify problems, e.g., increased error rates, latency spikes, unauthorized access attempts, before they escalate into major outages. Understand usage patterns. Gain insights into peak usage times, popular APIs, and client-specific consumption. Optimize performance. Pinpoint bottlenecks and areas for improvement in your API infrastructure. Plan capacity. Gather data to inform decisions about scaling resources up or down. Key metrics to monitor at the API gateway level include request volume, the total number of API calls processed per second, minute, or hour. This indicates traffic load. Latency response time, the time it takes for the gateway to process and return a response to a client. This is a critical indicator of user experience. Monitor both average and percentile latency, e.g., 99th percentile, to catch outliers. Error rates, the percentage of requests resulting in error codes, e.g., 4xx client errors, 5xx server errors. Spikes in error rates often signal issues. Throughput, the amount of data transmitted through the gateway in a given period. Resource utilization, CPU, memory, network I/O of the gateway instances themselves. High utilization can indicate a need for scaling. Cache hit ratio, For gateways utilizing caching, this metric indicates how often responses are served from the cache, reducing backend load. Security metrics. Number of blocked requests, e.g., due to rate limiting, failed authentication, WAF rules, suspicious activity alerts. Many API management platforms come with integrated monitoring dashboards that visualize these metrics in real time. Additionally, the gateway can often publish metrics to external monitoring systems, e.g., Prometheus, Datadog, New Relic, for centralized observability across your entire infrastructure. Logging. The digital breadcrumbs. While monitoring tells you what is happening, logging tells you why. Comprehensive logging provides detailed records of every event and transaction that occurs within the API gateway's domain. For each API request, valuable information to log includes timestamp, when the request occurred, client information, IP address, API key, application ID, user ID if authenticated, user agent, request details, HTTP method, URL path, query parameters, headers, response details, HTTP status code, response time, response size, error message, if any. Policy actions, which security policies were applied, any transformations performed, and whether a request was rate limited or blocked. Backend hops, which backend service received the request and its response status and latency. Best practices for logging. Centralized logging, aggregate logs from all gateway instances into a centralized logging system, e.g., Elk Stack, Splunk, cloud-native logging services. This makes searching, analyzing, and correlating logs across distributed systems much easier. Structured logs. Use structured log formats, e.g., JSON, to enable easier parsing and querying by automated tools. Contextual information. Include correlation IDs or trace IDs that link a single request's journey across multiple services, from the gateway to the backend. This is invaluable for debugging distributed systems. Security and privacy. Be mindful of sensitive data. Never log plaintext passwords or highly sensitive PII. Implement proper access controls to log data. Retention policies. Define how long logs are stored based on regulatory compliance and operational needs. Logs serve various purposes: troubleshooting and debugging. Quickly diagnose issues, understand request flows, and identify error sources. Security auditing. Provide an immutable record of access and actions for compliance and incident forensics. Usage analysis. Complement monitoring metrics by providing granular details for API usage patterns, client behavior, and billing. Alerting, proactive notifications. Monitoring and logging are passive unless paired with effective alerting. Alerts ensure that your operations team is immediately notified when predefined thresholds are crossed or abnormal conditions are detected. This enables proactive intervention before an issue significantly impacts users. Threshold-based alerts. High error rates, e.g., 5xx errors above 1% for 5 minutes. Latency spikes, e.g., average response time above 200 ms. CPU memory utilization exceeding a certain percentage. Low disk space on gateway instances. Sudden drop in request volume could indicate an upstream issue or outage. Anomaly detection alerts. Using machine learning to detect unusual patterns that deviate from normal behavior, even if specific thresholds aren't breached. Security alerts. Notification of repeated failed authentication attempts, suspected DDoS attacks, or WAF rule triggers. Best practices for alerting, clear and actionable. Alerts should clearly state the problem, relevant context, API name, metric, threshold breached, and potential impact. Avoid alert fatigue. Tune alerts carefully to minimize false positives. Too many alerts lead to operators ignoring them. Tiered alerting. Implement different severity levels with corresponding notification methods, e.g., critical alerts to pagers phone calls, major alerts to Slack email, informational alerts to a dashboard. Automated remediation where possible. For certain well-understood issues, e.g., high CPU, alerts can trigger automated scaling actions or restarts. Scalability and high availability. Building for resilience. The API gateway is a central component, so its ability to scale and remain available is paramount. If the gateway fails, your entire API ecosystem goes offline. Scalability. Handling increased demand. Horizontal scaling, preferred. Adding more instances of the API gateway to distribute the load. Most modern API gateways are designed to be stateless or near stateless and can easily scale horizontally. This involves running multiple gateway instances behind a dedicated load balancer. Autoscaling. Leveraging cloud provider autoscaling groups or container orchestration platforms, like Kubernetes, to automatically add or remove gateway instances based on demand, e.g., CPU utilization, request queue length. This ensures optimal resource usage and elasticity. Resource allocation. Ensuring gateway instances have sufficient CPU, memory, and network bandwidth to handle expected traffic loads. High availability, HA, and disaster recovery Doctor, minimizing downtime. Redundancy across zones regions. Deploying gateway instances across multiple availability zones within a cloud region or even across multiple geographic regions is crucial. If one zone or region experiences an outage, traffic can automatically fail over to healthy instances. Load balancer health checks. The load balancer distributing traffic to gateway instances continuously checks their health. If an instance becomes unhealthy, it's removed from the rotation until it recovers. Database configuration replication. If the gateway relies on an external database for configuration or state, e.g., API key management, ensure that database is also highly available and replicated. Graceful degradation. Designing APIs and the gateway to gracefully degrade performance rather than completely failing. For example, if a backend service is unavailable, the gateway might return a cached response or a meaningful service unavailable error, rather than a generic timeout. Automated backups and recovery. Regularly backing up gateway configurations and data sources with clear recovery procedures. Maintenance and updates. Keeping your gateway healthy. Just like any critical software, API gateways require regular maintenance. Security patching. Applying security updates and patches from the vendor or open source community promptly to address newly discovered vulnerabilities. Software updates. Keeping the gateway software and its underlying operating system up to date to benefit from new features, performance improvements, and bug fixes. Configuration management. Managing gateway configurations using infrastructure as code ISC tools, e.g., Terraform, Ansible, to ensure consistency, version control, and automated deployment of changes. Regular audits. Periodically reviewing gateway configurations, policies, and logs to ensure they meet security and operational standards. By diligently implementing these principles of operational excellence, monitoring, logging, and architecting for scalability and high availability, you transform your API gateway from a mere component into a resilient, performant, and intelligent backbone for your entire API ecosystem, ensuring your digital services are always on and ready to serve. Chapter 8, Navigating the Tool Landscape. Choosing the right API gateway and management platform. By now, you understand the critical role an API gateway plays in modern architectures and how comprehensive API management is essential for success. The market abounds with various solutions, ranging from open-source projects to full-featured commercial platforms and cloud-native services. Choosing the right API gateway and associated management platform is a significant decision that impacts your organization's agility, security posture, operational burden, and ultimately, its ability to scale its API strategy. There is no one-size-fits-all answer. The best solution for you will depend on a confluence of factors, including your organization's specific needs, technical capabilities, existing infrastructure, budget, and strategic goals. This chapter will guide you through the leading options and key considerations for making an informed choice. Key considerations when choosing a solution. Before diving into specific products, it's crucial to establish criteria based on your unique requirements. Deployment model, on-premise. Do you need to host the gateway within your own data center for stricter control, regulatory compliance, or to integrate with legacy systems? This requires more operational overhead. Cloud-hosted SaaS. Do you prefer a fully managed service where a vendor handles infrastructure, maintenance, and scaling? This offers convenience and often faster time to market. Hybrid. A mix of both, perhaps for specific workloads or to bridge cloud and on-premise environments. This often entails managing connections and possibly different gateway instances. Scalability and performance. How much API traffic do you anticipate now and in the future? What are your latency requirements? Does the solution support horizontal scaling and operate efficiently under high load? Features and capabilities. Core gateway features. Does it cover essential routing, authentication, authorization, rate limiting, and basic transformation? Advanced features. Do you need more sophisticated capabilities like protocol translation, complex data transformation, caching, circuit breakers, monetization, or advanced analytics? Developer portal. Is a built-in, customizable developer portal essential, or do you have an existing solution? Security. Does it integrate with your existing identity providers? Does it offer advanced threat protection, WAF features? Monitoring and analytics. What level of visibility do you need? Can it integrate with your existing observability stack? Ease of use and management. How easy is it to configure, deploy, and manage APIs through the platform? Is there a user-friendly GUI, robust CLI command line interface, or intuitive API for automation? What is the learning curve for your team? Integration ecosystem. Does it integrate well with your existing identity providers, CI/CD pipelines, DevOps tools, monitoring tools, and backend services? Are there connectors or plugins for common third-party services? Cost. Consider not just licensing fees for commercial products, but also operational costs, staffing, infrastructure for self-managed solutions, maintenance, and potential hidden costs. How is pricing structured? Per API call, per gateway instance features? Can it scale economically? Support and community. What level of vendor support is available for commercial products? For open source solutions, is there an active and supportive community? Are there ample documentation, tutorials, and training resources? Vendor lock-in. How easy would it be to migrate to a different solution in the future if your needs change? Categories of API gateway and management solutions. The landscape can generally be divided into three main categories. 1. Cloud-native API gateways, Platform as a Service, PaaS. These are managed services offered directly by major cloud providers. They are deeply integrated with the respective cloud ecosystems, offering seamless scaling, high availability, and pay-as-you-go pricing without the need to manage underlying infrastructure. Examples: AWS API Gateway, a highly scalable, fully managed service that handles hundreds of thousands of concurrent API calls. It offers capabilities like REST and WebSocket APIs, integrates with various AWS services, Lambda, EC2, ECS, supports custom authorizers, caching, rate limiting, and usage plans. Azure API Management, a turnkey solution for publishing, managing, securing, and analyzing APIs. It supports various protocols, REST, SOAP, has a built-in developer portal, rich policy engine for transformations and security, and integrates with Azure Active Directory. Google Cloud Apigee. While Google offers API Gateway as a simple proxy, Apigee is their full lifecycle API management platform, acquired for enterprise-grade capabilities. It provides advanced analytics, monetization, developer portals, and a sophisticated policy engine, suitable for large enterprises with complex needs. Google Cloud API Gateway. Google's lightweight, fully managed API gateway for serverless and cloud-native applications, often used with Cloud Functions or Cloud Run. It's simpler than Apigee but highly effective for specific use cases within Google Cloud. Pros: fully managed, minimal operational overhead, high scalability and availability, designed for cloud elasticity and resilience, deep cloud integration, seamless connectivity with other cloud services. Pay-as-you-go. Cost scales with usage. Cons: vendor lock-in, tightly coupled to the specific cloud provider. Limited customization, less control over the underlying infrastructure and software. Cost for high volume. Can become expensive at very high transaction volumes, though competitive at normal scales. Hybrid cloud challenges. may be less ideal for complex hybrid or multi-cloud environments outside the primary cloud's ecosystem. 2. Commercial API management platforms, self-hosted or SaaS. These are comprehensive, often enterprise-grade solutions offered by vendors specializing in API management. They typically provide an all-in-one suite covering the entire API lifecycle, from design and development to analytics and monetization. They can be deployed on-premise, in any cloud, or consumed as a SaaS offering. Examples: Kong Enterprise. Built on the popular open-source Kong Gateway, Kong Enterprise offers advanced security, analytics, developer portal, and lifecycle management features for large-scale deployments, often used in hybrid and multi-cloud environments. TIBCO Cloud API Management, formerly Mashery, offers robust API gateway capabilities, a strong developer portal, comprehensive analytics and monetization features, catering to enterprise clients. Broadcom, formerly CA Technologies, API Management, another enterprise-focused solution with strong emphasis on security, policy enforcement, and integration with legacy systems. MuleSoft Anypoint Platform, a comprehensive integration platform that includes a powerful API gateway and full API management capabilities, often chosen by organizations with complex integration needs. Pros: feature-rich, comprehensive suite covering the entire API lifecycle. Vendor support, dedicated customer support, and professional services. Cross-environment deployment. Many offer flexibility to deploy on-premise or in any cloud. Enterprise-grade, designed for complex organizational structures and varying compliance needs. Cons: higher cost, generally the most expensive option, with licensing fees and potentially significant infrastructure costs for self-hosting. Complexity: can be complex to set up, configure, and operate due to their vast feature sets. Resource-intensive, may require dedicated teams for management and maintenance if self-hosted. 3. Open-source API gateways. These solutions are driven by community development and offer high flexibility and cost-effectiveness initially. However, they require significant internal expertise for deployment, management, and ongoing maintenance. Examples: Kong Gateway Open Source, a lightweight, fast, and extensible API gateway built on NGINX and Lua. Offers core gateway features via plugins, authentication, rate limiting, logging. Very popular in cloud-native and Kubernetes environments. Apache API-SIX, a high-performance, open-source API gateway built on NGINX and LuaJIT, known for its dynamic routing and rich plugin ecosystem. TIC Open Source, another open-source gateway option offering a lightweight core with enterprise features available in its commercial version. Ocelot NetCore, a simpler, lightweight, and programmable API gateway for NetCore applications. Envoy Proxy, while primarily a service proxy for service meshes, Envoy can be configured as an edge proxy API gateway. It's often used as the data plane for other control planes like Istio, which handles internal service communication, but can extend to ingress. Pros: cost-effective, no licensing fees, though operational costs exist. High customization, full control over the codebase and configuration. Community-driven innovation, rapid development cycles and access to a vibrant community. Avoids vendor lock-in, greater flexibility to integrate with custom solutions or migrate. Cons: requires expertise. Significant internal operational and development expertise needed for deployment, maintenance, and extending functionalities. No dedicated support. Relies on community support, which might not be as immediate or comprehensive as commercial support. Feature gaps: may lack some of the advanced features, e.g., built-in monetization, advanced analytics dashboards, compared to commercial platforms, requiring custom development. Slower time to market. The initial setup and configuration can be more time-consuming. Strategic selection, aligning tools with your vision. The choice of an API gateway and management solution is a strategic one because it directly impacts your overall digital transformation and API strategy. Startups SMBs might initially lean towards cloud-native solutions for ease of use and low operational overhead, or a lightweight open-source gateway for cost control and flexibility. Growing companies. may find commercial SaaS offerings or open-source solutions with commercial backing, like Kong Enterprise, appealing for their balanced features and support. Large enterprises often require the comprehensive features, robust security, and deep integration capabilities offered by enterprise commercial platforms, or could opt for cloud-native solutions if heavily invested in a specific cloud provider. Before committing to a solution, it is highly recommended to conduct a proof of concept POC. Deploy selected candidates in a limited environment, test their core functionalities against your specific requirements, and assess their performance, ease of configuration, and team's comfort level. Engage key stakeholders, architects, developers, operations, and security teams in the evaluation process. The API Gateway and its overarching management platform will be the central nervous system of your public-facing digital assets. Choosing wisely will pave the way for a secure, scalable, and successful API journey, enabling your organization to unlock new opportunities and thrive in the API economy. Chapter 9. The Evolving API Landscape. Advanced Patterns and Future Trends. The world of APIs is dynamic. What was cutting-edge yesterday is standard today, and new challenges and opportunities are constantly emerging. As you build and manage your API ecosystem, it's essential to look beyond current best practices and understand the advanced patterns and future trends that will shape the next generation of digital interfaces. The API Gateway, while a mature technology, is not static either. Its role is expanding, adapting to new communication paradigms, architectural styles, and demands for greater intelligence and automation. Beyond REST, new communication patterns for APIs. While REST-TFL APIs remain dominant, particularly for web clients and public interfaces, the API landscape is diversifying to address specific performance, efficiency, and real-time communication needs. GraphQL, what it is: a query language for your API and a server-side runtime for executing queries by using a type system you define for your data. Unlike REST, where clients consume fixed endpoints, GraphQL allows clients to request exactly the data they need and nothing more in a single request. Why it's emerging. Solves common REST problems like underfetching, multiple requests to get related data, and overfetching, receiving more data than needed. Ideal for mobile applications or complex UIs that need tailored data shapes. Gateway implications. API gateways are evolving to support GraphQL. This can involve GraphQL Gateway Proxy, a gateway that acts as a GraphQL endpoint, federating requests to multiple backend services that might be REST, SOAP, or even databases. GraphQL Schema Stitching Federation, combining multiple GraphQL schemas from different services into a single unified schema at the gateway level, making it appear as one large graph to clients. This allows microservices to own their own specific data graphs while presenting a cohesive API. gRPC, Google Remote Procedure Call, what it is: a high-performance, open-source RPC, remote procedure call framework that uses protocol buffers, a language-agnostic, platform-agnostic, extensible way of serializing structured data, as its interface definition language, IDL, and HTTP2 for transport. Why it's emerging. Built for efficiency and speed. Ideal for inter-service communication, microservices, real-time streaming services, and mobile applications where bandwidth and latency are critical. HTTP2 brings benefits like multiplexing, multiple requests over one connection, and header compression. Gateway implications. Traditional HTTP Point 1 based gateways need to adapt to gRPC's HTTP2 foundation. Dedicated gRPC gateways or extensions to existing gateways are emerging to handle. Protocol translation. Exposing gRPC APIs as REST JSON to external clients, gRPC to REST transcoding, or vice versa, allowing clients not supporting gRPC to interact with gRPC backends. Streaming support. Managing the long-lived connections for bidirectional streaming inherent in gRPC. Event-driven architectures, EDA, and webhooks, what it is. Instead of clients constantly polling for updates, request response, EDAs involve systems emitting events asynchronously and other systems subscribing to those events. Webhooks are a common way to deliver real-time notifications to external systems, where a service makes an HTTP post request to a URL provided by a client upon a certain event. Why it's emerging. Enables real-time experiences, reduces polling overhead, and decouples systems. Ideal for use cases like fraud detection, real-time analytics, or notifications. Gateway implications. While not a traditional request to the gateway, gateways can play a role by validating webhook payloads, ensuring incoming webhook events are legitimate and adhere to a schema, securing webhook endpoints, authenticating event sources and ensuring webhook delivery is secure, routing and fan-out, routing events to potentially multiple internal subscribers or external webhook consumers, event monitoring, providing visibility into the flow of events, the rise of service mesh, a complementary ecosystem. As discussed in Chapter 2, service mesh technologies, like Istio, Linkerd, Console Connect, are gaining significant traction in microservices environments, particularly those deployed on Kubernetes. A service mesh provides capabilities for traffic management, security, and observability for internal, service-to-service communication. Complementary, not competing. An API gateway manages ingress traffic, north-south, into your system, acting as your front door. A service mesh manages internal traffic, east-west, between your microservices once the request is inside. Decoupling concerns. The API gateway continues to be crucial for API productization, external developer experience, and managing traffic from the public internet. The service mesh handles the operational complexities of internal service communication, freeing your microservices from implementing features like MTLS, retries, or circuit breakers. The future integration. We're seeing closer integration between API gateways and service meshes. For instance, the gateway might offload internal routing and policy enforcement to the service mesh once a request passes through the main, front door. This allows each component to specialize in its core competency. API gateways as an integration layer, a new identity. The traditional role of an API gateway is evolving. Beyond being a simple proxy, it's increasingly becoming an intelligent integration layer that can. API orchestration composition. Stitching together calls to multiple backend services into a single API endpoint to simplify client-side development. This is especially useful for older, more granular backend APIs. Business logic enforcement. Applying light business logic directly at the edge, rather than on the backend, for performance or specific use cases. This can include data enrichment or simple decision-making. Data virtualization. Presenting a unified, virtualized data layer to consumers, abstracting away the complexity and diversity of underlying data sources, databases, legacy systems, other APIs. The intelligent edge, AI, ML, and automation. The API gateway is poised to become smarter, leveraging artificial intelligence and machine learning. Predictive analytics. Using AI, ML to anticipate traffic spikes, identify unusual access patterns that could signal an attack or predict system failures. Automated policy adjustment. Dynamically adjusting rate limits or security policies based on real-time threat intelligence or observed traffic anomalies. Enhanced security. More sophisticated anomaly detection for API security, moving beyond signature-based WAFs to behavioral analysis. Automated remediation. Triggering automated responses to detected threats or performance degradation without human intervention. AI Ops, artificial intelligence for IT operations. API gateway data feeding into AI Ops platforms for intelligent correlation, root cause analysis, and self-healing systems. API gateways and serverless architectures. Serverless computing, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, relies heavily on APIs as the primary interface to trigger functions. Native integration. Cloud-native API gateways are often tightly integrated with serverless compute services, providing the necessary routing, authentication, and request handling for serverless functions. Reduced operational burden. Pairing a managed API gateway with serverless functions provides a truly zero-ops API deployment, where the cloud provider manages virtually all infrastructure. The future of API management, consolidation and specialization. The trend suggests both consolidation and specialization. Consolidation within suites. Comprehensive API management platforms will continue to offer broader capabilities, integrating more advanced gateway features, improved developer experiences, and deeper analytics under a single umbrella. Pervasive gateways. Gateways will become even more ubiquitous, running not just at the edge, but potentially closer to microservices, within a service mesh context, or even embedded within applications for specific purposes. API-first everything. The API-first mindset will continue to gain traction, where APIs are designed and treated as primary products or interfaces from the outset of any software development project. The API landscape is expanding rapidly, and remaining competitive requires continuous adaptation. API gateways are at the forefront of this evolution, stretching their capabilities to handle next-generation communication protocols, integrate with emerging architectural patterns, and leverage intelligence for proactive management. Embracing these advanced patterns and trends will ensure your organization's API strategy remains agile, secure, and ready for whatever the digital future holds. Chapter 10. Mastering Your Digital Presence. A strategic approach to API success. Throughout this book, we've journeyed from understanding the fundamental role of APIs in our interconnected world to dissecting the intricate anatomy of the API gateway, exploring its myriad features, and delving into the comprehensive discipline of API management. We've highlighted the paramount importance of developer experience, the non-negotiable need for robust security, and the critical role of operational excellence. Finally, we peered into the future, anticipating the next wave of communication patterns and intelligent capabilities. So, where do you go from here? How do you distill all this knowledge into actionable steps to ensure your organization masters its digital presence through APIs? It boils down to adopting a strategic, holistic, and continuous approach. 1. Embrace an API-first mindset, driven by business strategy. The most crucial step is to view your APIs not merely as technical interfaces, but as digital products that serve specific business objectives. Start with why. Before designing any API, define the clear business problem it solves. Are you enabling new revenue streams, improving operational efficiency, fostering partnerships, enhancing customer experience? The why should always precede the how. Design for consumption. Treat your API consumers, internal developers, partners, external developers as your customers. Design APIs that are easy to understand, consistently structured, well-documented, and reliable. This developer experience, DX, is a direct reflection of your business agility. Govern with intent. Establish clear API governance policies from the outset. This includes naming conventions, data standards, security protocols, and versioning strategies. Consistent governance prevents API sprawl and ensures a cohesive developer experience across your entire portfolio. 2. The API Gateway, your cornerstone of control. The API Gateway is not just a tool. It's the central enforcement point for your API strategy. Centralize policy enforcement. Leverage the gateway to uniformly apply security policies, authentication, authorization, threat protection, enforce traffic management rules, rate limiting, caching, and perform necessary transformations. This reduces complexity for backend teams and ensures consistency. Shield and protect. By acting as a single entry point, the gateway shields your valuable backend services from direct exposure, providing a critical layer of defense against malicious attacks and unauthorized access. Gain visibility. Position the gateway as your primary data collection point for API monitoring and analytics. The insights derived from gateway logs and metrics are invaluable for understanding usage, performance, and security posture. 3. Comprehensive API management. Beyond technology. API success requires more than just a gateway. It demands a full lifecycle approach. Invest in a robust platform. Whether it's a cloud-native service, a commercial suite, or a well-managed open-source solution, choose an API management platform that scales with your needs and supports the entire API lifecycle, from design and development to publishing, monitoring, and deprecation. Build a great developer portal. This is your API showroom and self-service hub. Make it intuitive, comprehensive, and engaging. Provide clear documentation, code samples, interactive tools, and easy access to support. Foster a community. Encourage interaction among your API consumers. Provide forums, Q&A sections, and direct support channels. Listen to feedback and iterate on your APIs based on user needs. 4. Security as a culture, not an afterthought. Security is a continuous journey, not a destination. Assume breach. Design your API security with the assumption that your systems will eventually be probed or attacked. Layer your defenses. Use the API Gateway's robust security features. Secure your backend services, implement network segmentation, and manage secrets carefully. Continuous vigilance. Regularly monitor your gateway logs for suspicious activity. Conduct frequent security audits, vulnerability scanning, and penetration testing. Stay informed about emerging threats and quickly patch any discovered vulnerabilities. Educate your teams. Ensure all teams involved in API development and operations are well-versed in API security best practices. Developers are your first line of defense. 5. Prioritize operational excellence. Reliability, performance, and scalability are non-negotiable for critical APIs. Monitor everything. Monitor the health and performance of your API gateway and backend APIs obsessively. Establish clear metrics, set up actionable alerts, and implement robust logging. Design for resilience. Architect your API gateway deployment for high availability and disaster recovery. Utilize horizontal scaling, redundancy across availability zones, and automated failover mechanisms. Automate, automate, automate. Automate the deployment, configuration, testing, and scaling of your API gateway and APIs using infrastructure as code ISC and CI/CD pipelines. This reduces manual errors and accelerates time to market. Plan for growth. Build your API infrastructure with future scalability in mind. Consider how it will handle peak loads, new features, and increasing numbers of consumers. 6. Adapt and evolve. Embrace the future. The API landscape changes rapidly. Staying competitive means staying current. Monitor trends. Keep an eye on emerging communication patterns, GraphQL, gRPC, event-driven APIs, architectural styles, service mesh, and technological advancements, AI ML in operations and security. Pilot new technologies. Don't be afraid to experiment with new gateway features or API paradigms in controlled environments. Early adoption can provide a significant competitive edge. Continuous improvement. APIs are living products. Gather feedback, analyze usage data, and continuously iterate on your API designs and implementations. The API lifecycle is not linear. It's a continuous loop of design, build, deploy, manage, monitor, and improve. Final thoughts: your APIs, your digital destiny. In today's hyper-connected world, APIs are more than just technical connectors. They are the fundamental building blocks of digital business, innovation, and strategic partnerships. Your API gateway is the control tower for this digital frontier, providing the necessary visibility, security, and performance. However, the true value of your APIs is unlocked not just by the technology itself, but by a holistic, strategic approach to API management. By deliberately focusing on the business value of your APIs, empowering developers with excellent experiences, rigorously enforcing security, ensuring operational resilience, and remaining agile in the face of evolving trends, your organization can move beyond merely being present online to truly mastering its digital presence. The journey to API success is ongoing, but with the right strategy and tools, your organization is well equipped to navigate the complexities and seize the immense opportunities of the API economy.